Did you know that in the UK, someone has an asthma attack every 10 seconds, and that of these people, 3 will die each day? Aerosol drug delivery devices are widely used in the treatment of respiratory and systemic diseases, including asthma, and their effectiveness can be the difference between life and death. I'm Toria, and I'm looking forward to introducing you to my PhD project, which hopes to improve the efficiency of inhaled therapeutics using particle engineering approaches and computational modelling. When someone uses their inhaler, the aerosol drug particles transition from ambient conditions into the 37.5 degrees Celsius and 99.5% relative humidity of the respiratory system. Upon entering this environment, drug aerosol particles may transform through dissolution or hygroscopic growth, which can then affect their deposition and uptake, and ultimately patient outcomes. The extent of these transformations is dependent on the ambient humidity prior to inhalation, and the physicochemical properties of the particles themselves, such as their size, composition, or crystallinity. As such, my PhD will involve developing a microcrystallizer system capable of producing monodispersed drug particles with tunable characteristics, using a combination of microfluidics, spray drying, and anti-solvent crystallization techniques. This is to study and quantify how an aerosol's physicochemical properties affect their interaction with water vapor in the lung. I'm also developing a hygroscopic deposition model capable of predicting the regional and total deposited drug dose, and this is the focus for the remainder of this talk. To be effective, inhalers must deposit drug in sufficient concentration within target regions of the respiratory system, and we can use computational models to help us study this. However, many current models do not account for particle hygroscopicity, or how initial ambient humidity and aerosol size may influence this. In response, we've developed a model combining the heat and mass flux equation proposed by Kamala et al. With the ICRP deposition model, a commonly used dosimetry model that divides the respiratory system into distinct regions. We use this equation by Kamala to simulate the hygroscopic response to the equilibration of 2 distributions of glycerol droplets into 20 or 90% RH and the subsequent inhalation. We then extracted the aerosol diameters from the simulation at times matching the residence times of the ICRP regions, and used these to calculate the regional deficit fraction. In doing so, we found that the smaller size distribution exhibited higher deposition in every region. Furthermore, droplets equilibrated 98% RH showed increased extrathoracic deposition, but reduced hygroscopic growth and deep lung deposition in comparison to the 20% RH equilibrated droplets for all size distributions. This is in part due to the larger size at the point of inhalation. As our previous work demonstrated that water condensation onto evaporating PMDI droplets yields a droplet water activity of 0.98 upon exit from the device, these results may have interesting implications for the inhalation of PMDI directly versus through a spacer device, which can be likened to our 98% or 20% RH environments respectively. However, further research is required before strong conclusions on this can be drawn. Thank you.